about the one-way analysis of variance, which is ANOVA test. And through ANOVA test, we can test the equality of the population's means when we have two or more populations. So I have opened few data files here for the tutoring purpose, and you can see here this is aflatoxin file, so that you can understand what sort of the data shape is required to run the analysis of variance. So there is a stacking form of the data. You can see here all the values are lying in one column, which is toxin, and that variable which is independent variable, that is indicating that these 16 values are from the population 1, and the next are from the population 2, 3, and so on up to the population 8. So we have 8 different types of the population yield where these samples have been collected. So to run the ANOVA, we need a stacking form of the data where the dependent variable or the study variable, all the entries are lying in the single column. So I can share you another file here, that is behavior. So if you want to run the analysis of variance to this data, you cannot apply because this type of the shape is not appropriate to run the ANOVA. And for that purpose, you have to rearrange all these observations so that all these scores are lying in one column, whereas the independent variable should be mentioned in the other column. And just for your ease, I have arranged all these values, and for the example I have just taken for 6 values. So here you can see all these scores are lying in a single column, and the behaviors are shown in the dependent variables. So these are all score related to the run, write, read, etc. So that is basically requirement, the data requirement to run the analysis of variance. So coming back to the aflatoxin. So the main assumption to run the analysis of variance is the normality, and how to test the normality of the data. There is another video, normality test. You must watch that video to see how we can test the normality of the data. So since I have tested so many times the normality of the data, and all these yield types are following normal distribution, so I'm not including the normality test in this video. So directly moving to apply the one-way analysis of variance. So here you have to go to the path, we analyze, and then we have compare means, and then we have one-way ANOVA. So once you have this dialog box, you will select the main study variable under the dependent list, and the cone yield would be under the factor, that is the independent variable here. So keep in mind that the variable that is containing the codes is selected under the factor, whereas the main study variable is selected in the dependent list. And now clicking the options button here, and while clicking the option buttons, you can have the descriptive measures for all these samples, and then homogeneity of variance test. So by clicking the homogeneity of variance test, we can also test the equality of the variances for the given data, and then continuing here, and then clicking this OK button. So you will see an output. So this is the output window. In the output window, since we checked the descriptive button or the checkbox, so descriptive measures related to the all yields are lying over here, and the standard deviation and the other descriptives are lying. And the next table, you can see here Leibniz test for the equality of variance, and this test is significant. It means all these variances are not equal. Maybe some of the variances are same, but few are different. And the next step is ANOVA, which is testing our main hypothesis for the equality of means of all these 8 yields. So it is showing the significance as well, since the p-value is less than 0.05 here as well as here. So in the analysis of variance, You can test two types of the hypothesis. One, the quality of the variances of all the given data samples, and the ANOVA test would be testing the quality of the means of the given data samples. And now I take you to another document uh, where I have uh, tested the master variance on some portions of the data so that you can understand the other portions. But before moving to that, we have another test within the scope of the master variance, that is a post hoc. Post hoc tests are applied in case this ANOVA is showing you the significance. When this is significance, it means all the means are not equal. Few of the pairs of the means may be equal and few are not. So just to see which of the pairs are significantly different, you can have the post hoc test. The post hoc test, you can use this path. So the same as used earlier, that analyze, compare, mean, analysis of variance, and then we have to click here the post hoc button. So in the post hoc button, you can see here on this dialog box, it has two portions. It will be accommodating the cases when the variances are equal and the cases when variances are not equal. And how we come to know whether the variances are equal or not equal, that your Leibniz test would be helping us in judging. So in this case, your Leibniz test was significant. So whenever this Leibniz test is significant, it means all the variances are not equal. So when the variances are not equal, you can choose here the post hoc tests from these four given tests. And in case the variances are equal, so you can make a choice from these tests. So here in particular case that we have analyzed, I'm using here the Tamhanis T2, and then checkbox is filled, and now continuing, and then pressing the OK button. So you will have the earlier tables that we obtained earlier, and with all these tables you can have these post hoc tests. So here this is the output of the post hoc test. Here you can see here one-to-one comparison. One-to-one comparison means the yield number 1 is being compared with the yield number 2, and then yield number 1 with yield number 3. And similarly, the yield number 1 has been compared with all the remaining 7 yields. So here you can see in this portion the yield number 2 has been compared with the rest of the yields, and similarly yield number 3, 4, etc. And now which of the pair of the means are significantly different? You see here the small asterisk is appearing here, and in case you are confused with the asterisk, you can see the corresponding p-value. Here you see the p-value is 0.023, and since the p-value is less than 0.05, it means it is significant, and significant mean the mean of yield number 1 is not equal to the mean of yield number 2. So that's how we can pick all the possible pairs where the means are not equal, and where you can see the asterisk is not appearing and the p-value is greater than 0.05. So this is the possible pair, which is mu1 and mu7, where means are equal. So in case the significance is there, the pairs are not equal, and in case it is non-significant, mean the p-value is greater than 0.05, it means that pairs of the means are equal. So that's how you can evaluate or interpret this table, which is the post hoc test. And now taking you to the subset of the data where I have selected fewer yields. So here it is. This is example number 1. So here I have selected only 5 to 8 yields. In the last 4 yields I am including in this analysis of variance. And if you want to know how to make the selection, there is another video lying on the channel, that is select cases. So if you watch this video, you will understand how to make a selection from the given data if you want to select the fewer uh, or the subset of the data to analyze. So to test the and also variance on the yield number 5 to 8, first we see what is the hypothesis for the one-way analysis variance. So here it is. This is null hypothesis that mu5 equals mu6 equal mu7 and up to the mu8. And against the alternative hypothesis would be at least one mean is different. Means not all means are different. In case at least one mean is different, we can't say that all means are same. So that's why we here mention that at least one mean should be different in the alternative hypothesis. So this is the descriptive output if you run the ANOVA. And next to it is the homogeneity of variance. So you see here is a significant, mean all these variances are not equal. So you see what can be the possible set of hypotheses for the variance test. So here it is in the yellow box. You see the null hypothesis sigma 5 square equals sigma 6 square equals sigma 7 square. In all these variances are equal. So here since the p-value is significant, it means not all variances are equal. And the mean and also variance table also it is significant, mean the means are also not equal. So in this data, neither the variances are equal nor the means of these four yields are equal. And now, since your ANOVA table, ANOVA test is significant, you should go for the post hoc test. And post hoc test choice is made according to the result of the equality of the variance. So here is the corresponding dialog box where you can make a choice of the uh, test which is appropriate in the situations. So since the variances are not equal, so we have to make a choice from this portion of the dialog box. So the TAM honey has been selected here for the post hoc, and this is the output of the TAM honey. So you can see here each of the yield has been compared with the remaining three yields. Since the four yields were selected in this analysis of 5 versus 6, 5 versus 7, 5 versus 8. So similarly, the case where the asterisk is appearing, so these are the all cases where the means are not equal. And here I have summarized all the pairs. You see here the yield number 5 versus the yield number 6. This is non-significant. Why? Because the p-value is greater than 0.05. It means the mean of yield number 5 and mean of yield number 6 are equal, mean the same. And in other cases, the yield number 5 versus 7 is significant, and why it is significant is the p-value is less than 0.05. And moreover, you can see here the asterisk is appearing. So an asterisk is indicating that this pair is significant. So I have chosen all these possible pairs which are related to this output. So the case where there is significance and there is a non-significance you see here. And now for another example, here I have made a selection where the 4, 6, 7 and 8 yields have been chosen for the running of one-way analysis of variance. So similarly, when you run this analysis, first of all you can have the descriptive table. So this is a descriptive table, and then afterwards we can have homogeneity of variance, and then the ANOVA test, which is for the equality of the means. So you see here this is insignificant. So the p-value is greater than 0.05, which is 0.705, which is far greater than 0.05. You can say that your variances are equal. And this is the interpretation in the yellow box. So the variances are equal, but the means are not equal. So whenever the means are not equal, you can go for the post hoc tests. And now since the variances are equal, I have chosen here some of the tests from this dialog box when equal variances are assumed. So here in this particular analysis, I have selected LSD test and Duncan's test. And the output you see here for these four yields are, this is LSD output. So LSD output is same as Tam-Hanes T2. So if you know the interpretation of the Tam-Hanes T2, it's understood that you know the interpretation of LSD, since the layout of both the tables are quite similar. And now after that we have the result of the Duncan's output table. So you can see here. So it's the beauty of the Duncan that Duncan divide or distribute the data in different subsets. So here we have four subsets, and these subsets contain the yield types or the populations whose means are alike. So here you can see under the subset 1 we have only one yield, which is yield number 8, and in the subset number 2 we have yield number 4, in the subset 3 we have yield number 7, and in the 4 we have yield number 6. In case these two yields are lying under the same subset, it means these two yields are same in the population mean. But in this particular situation, in none of the subset we are having two or more population means. So we can say that all these four populations, that is the yield number 8, yield number 4, yield number 7 and yield number 6, have different means. Mean their means are quite away from each other, and no, there is no any possibility to say that the two yields are, you can say, the same. They are not same. So all these yields are different from each other. In case you can apply the Duncan's test, you can have multiple type of the output, and their interpretation would be accordingly. So if you go through all these notes, so you can understand it, that how to interpret the Duncan's tables.